All right, IB students, this is my first time trying one of these videos, so hopefully it works out okay. It's a video about Lewis structures, topic 4.3 from the IB Chem Guide, which says Lewis, or electron dot structures, show the electron domains in the valence shell and are used to predict molecular shape. Now, I wanted to read out that as essential idea for you guys because there's some terminology here that comes up often in the IB textbook, but just like a lot of things with IB, it's not necessarily the terminology that I am familiar with or that I use when I'm describing things. I tend to be a bit colloquial. So just know that sometimes I'll be talking about electron pairs or lone pairs or things like that, but IB prefers the term electron domains, okay, which doesn't mean exactly the same thing as lone pairs, but we'll get to that in the next video, which will be about Vesper theory. Okay, but that's kind of it. So let's look at sort of the specifics from the Chem Guide. So the stuff in red is what's going to be covered today. I'm going to go over how to draw Lewis dot diagrams. Now, those of you who were in class on Monday already saw me do a couple Lewis diagrams. So you might be able to sort of glaze over the first couple minutes of this video. But then we're going to get into, so we're going to do sort of the basics, simple Lewis structures where the octet rule is followed and maybe there's some multiple bonds, but things don't get too complicated. But then we're going to look at some other things, exceptions to the octet rule, including contracted octets, expanded octets. We're going to talk about resonance structures. And then we'll talk a little bit about how we'll do some examples where there's an ionic charge and how that might factor in. All right. So let's look at our first example here. Now, going forward, it's maybe not a bad idea for you to have a piece of blank paper in front of you just so you can make some jot notes. I might even suggest that you pause the video and try a couple things before moving forward, just because I really do think that sort of activity helps you to stay engaged with the content, so you're not just like kind of glazing over and falling asleep while you're watching the video. So have a blank piece of paper and something to write with, and maybe pause the video, try a couple of the examples before seeing what my answer is. Okay, so the first thing we're going to do is a simple Lewis structure for the molecule carbon tetrachloride, CCl4. So my first step when I want to make a Lewis structure is to total up all the valence electrons. Okay, and to figure out the valence electrons, you can look at a periodic table, so you might want to have one of those on hand as well. You can pause a video and track one down, or you can maybe flip to a tab on your computer when you need one. And to figure out the number of valence electrons, because with Lewis structures we're almost always going to be dealing with nonmetals, you just look at the group number, and then you subtract 10 from that to get the number of valence electrons. So for example, with carbon, it's in group 14, so it has 4 valence electrons. Similarly, chlorine, group 17, each chlorine brings 7 valence electrons. So that gives me 4 from the carbon plus 7 from each of the 4 chlorines. I get a total of 32 valence electrons. Okay, and now you may have learned a little bit about drawing Lewis structures in grade 10. Often, when you're first learning these, you emphasize a little bit like where the electrons are coming from, which element they come from. But to be honest, at this point, I just want the total. It doesn't really matter which element brought more electrons with it. You just need to know how many electrons you have available. So that's what we have for carbon tetrachloride. We have 32 electrons that will be represented in our final Lewis diagram. The next thing we need to do is arrange the element symbols in some logical way, okay? Because I'm making a 2D representation of my carbon tetrachloride molecule, so I need to sort of figure out what that's going to look like. A good guiding principle is if you have sort of an obvious central atom, it's going to be the element that has a lower electronegativity. And you can look that up in table 8 of your data booklet if you want, or you can sort of remember the general trend that we talked about in class, which is that electronegativity tends to be higher at the top of the periodic table and higher towards the right of the periodic table. So if you use those sort of guiding principles, you probably recognize that chlorine has a higher electronegativity than carbon. So we put the element with a lower electronegativity in the middle, and then we put the higher electronegativity elements around it, like that. Okay? Our next step is to start adding in some electrons. Now, you do have some flexibility with how you represent Lewis or electrons in Lewis structures, but I like to do it a certain way. You don't have to follow exactly how I do it, but that's how you're going to see me doing it. So the first thing you want to do is draw single bonds between adjacent atoms. So that's going to look like this. And I always represent my single bonds as sticks. Some people will use dots or even 1 dot 1 X to represent different electrons coming from different spots. I think that looks a little messy and it gets a little bit confusing, so I prefer just sticks. But if you want to use dots, that's on you. The next thing you're going to do is fill the valence of each element so that it's following the octet rule. And for now, that's going to be our guiding principle, right? The octet rule, every element needs 8 electrons around it. Okay, so each chlorine has 8 electrons now, and then carbon, because it has 4 bonding pairs, also has 8 electrons around it. Okay, so maybe pause the video for a second, make sure that you agree that there are 8 electrons around everything. Okay, so now I want to count up my total. I want to see if the electrons I have represented in my diagram match the number of electrons I was allowed, which is, if you look back here, 32. So, I'm going to give you guys a second. I'm going to say pause the video, see if you get 32 electrons in that diagram right there. And hopefully you do. I usually try to count in multiples of 8, so I go, oh, there's 8 around each chlorine, and I've got 4 chlorines. 8 times 4 is 32. It's kind of an easy way of checking the total. Okay, so we're done. That's it. As long as you sort of follow these rules, and when you get to the end, your electrons represented match the electrons you started with, you're good. We can move on to another example. So here's one where we're going to end up with multiple bonds. Carbon dioxide. You probably already know what the Lewis structure of carbon dioxide looks like because you maybe have seen it before. And that's okay. We're still going to go through the steps. One thing that I am going to suggest, if you're not already practicing these with a pencil, it's a good idea to use a pencil because when we need to include a multiple bond, often we need to go back and erase electrons that we drew already. Not a bad idea to use a pencil so you can do that. So, I'm going to do the same thing I did before. I'm going to total up the valence electrons. So I have 4 from carbon because it's in group 14. I have 6 from each oxygen because they're in group 16, and that gives me a total of 16 electrons. Then I'm going to arrange the element symbols in a logical way using that general rule about electronegativity. Oxygen versus carbon. Oxygen is more electronegative, so I'm going to put carbon in the middle, and then I'm going to put the oxygens on either side. Then, this is where things maybe are a little frustrating because you probably have a picture in your head of what carbon dioxide is going to look like, but I'm going to go through the steps here. I'm going to just put single bonds between adjacent atoms, like that, and then I'm going to fill everything's octet so everything has 8 electrons around it. So that's going to look like this, and like this, and like this. Okay? I know, we both know that's not correct, but just fill it in for now. It's part of the process. Okay, so now we're going to check the total. We're going to count up the electrons, and probably you already see that we've got more than 16 here. We've actually got 20, which is not the number of electrons we started with. I'm allowed 16. Right now in my diagram, I've represented 20. So, if I need to reduce the number of total electrons, to do that, I am going to erase non-bonding pairs on 2 adjacent atoms, and then I'm going to replace those with a bonding pair. So I took away 4 electrons there, and then I added 2 back in. Okay? And then if you double check the total now, you'll hopefully see that we reduced the number of electrons down to 18, which is still too many. We need 16. So I'm just going to repeat that process again. Okay? And probably you kind of see how that's going to work. I take away 2 on carbon, 2 on oxygen, and I replace it with a double bond. And then I have this nice symmetrical carbon dioxide Lewis structure. Okay? And that's it. Okay, I'm going to pause it here because that's about 10 minutes, and I'm going to make a version number 2, or a video number 2 for the next few slides.